So they're asking us to find the family of curves that are orthogonal to the family y equals to kx, where k is just an arbitrary constant. So in the same way that we did last time, let's just find the derivative of this function. That's dy dx equals to k times the derivative of x, which is just k. Alright? So we're done with the derivative here. However, we want to write this k in terms of x and y. So what we can do here is solve for k. That's going to give us a y over x. So dy dx then will be, well, replaced with this quantity k. Now, so since this is y over x, what's this ultimately? So this is the slope of a family of linear functions. How do we know that these are linear functions? Well, because check this out, y equals kx, that's basically a family of linear functions. We have the variables x and y both to the first power, so that has to describe a linear function, and that k, well, depending on the value, that's going to give us different slopes. So now we want to find out the family of orthogonal trajectories. So in this case, let's orthogonalize and by orthogonalizing we mean to find the opposite in sign and reciprocal of this derivative that we had. Again, that comes back from the definition of having slopes of orthogonal or perpendicular lines. Again, it's always the opposite in sign and reciprocal of it. So this will be itself dy dx. But what we do in this case is find the reciprocal x over y and opposite in sign. So what we have to do here is the following. So that's multiply both sides by y dy. So we have to solve the differential equations. In other words, negative x dx. So now that we separated the variables, well, we may go about the integration of the equation. So that is, integrate both sides, y squared over 2. Recall that we don't do a plus c on the left hand side. We only do it on the right hand side by the process called absorption. And minus x squared over 2 plus c. So here is where we add that plus c. Well, so you might want to solve, or rather to have all the variables on the right hand side of the equation, on the left hand side. So that's going to give us x squared plus y squared over 2 equals to c. And well, so you might want to clear the denominators by multiplying by both sides by 2, and that becomes x squared plus y squared equals, well, recall that when we multiply an arbitrary constant by any number, that's just the arbitrary constant c in this case. Alright? So, well, so what kind of graphs do this generic equation describe? Anyone? Circles, right? Circles of radius, well, whatever that radius are. Right? So what do we have in this case? So we have circles. One circle here, another circle there, and then another here. And we also have diagonal lines. Lines that actually pass through the origin. And we can have many possibilities here. In fact, this picture matches the one in the definition here, right? Which is when we define what orthogonal trajectories were. So again, we're concluding that a family of lines is orthogonal to a family of circles and vice versa. All right? So that's how we get the family of orthogonal functions. Let's move on to the next topic, mixing problems. Well, so the idea is that we have this big tank, right, in which a mixture is going on, and it could be water with sugar, water with salt, which we call typically we call it brine, you know. Mixing beer, you know, when you want to come up with a blend of beer, different beers with different alcohol percentages, and you want to use this process to obtain certain mixture or certain alcohol level or certain concentration of a solute salt, you know, or sugar, depending on the purpose here. So what's going to happen? So the rate of change between the quantity A and with respect time, it's going to be the difference between the rate. So whatever comes in minus whatever comes out. So you know, so because this is coming out, that's why we are subtracting that quantity. And well, we further describe the rate in and rate out as the flow in rate times the concentration, and the flow out rate times the concentration. So I think an example here would be a good way to see this in action. So let's have a look at the next example. So a tank contains 1,000 liters of brine, which is with 15 kilograms of dissolved salt. Pure water comes in. This is key, pure water. Let me highlight it. And at a rate of 10 liters per minute. The solution is kept thoroughly mixed and drains at the same rate that comes in. All right, that's another piece of information that you want to keep in mind. The solution is kept thoroughly mixed at the same rate. How much salt is in the tank after T minutes? So they're asking us an expression, or a function rather, that can help us calculate the amount of salt that remains inside of the tank at any time T. So number one, let's draw a picture. So we have this tank. Let's assume it's a cylindrical tank for the sake of simplicity. All right, and what do we have? We have something coming in, and we have something coming out. So whatever comes in, it's pure water. It's pure water at a rate of 10 liters per minute. Okay, so it's pure water. What's coming out? At the same rate, it's coming out at the same rate, 10 liters per minute. And what do we have? We have the mixture water and salt. And we have that mixture of these two species here. So now, here is the thing. What's inside? Inside we have 15 kilograms of salt. And I think that's all the information that we need. Well, of course, the tank is 1,000 liters. It has a capacity of 1,000 liters in volume. All right, so let's set up the equation that will help us calculate an expression that gives us the amount of salt at any particular time. So we're going to start with dA dt equals number one, rate in minus rate out. And well, again, the reason why we have the rate in positive is because that's coming into the tank, and the reason why we have the rate out as negative, that's because it's coming out of the tank. And well, so in this case, let's further break this up, or break this down as a rate in. That's the flow rate in, or flow in rate rather, times concentration in minus flow out rate times concentration out. Okay, so let's see. Flowing rate. They're telling us the numerical value of the rate at which whatever is coming in, right? So dA dt, this means, so the flowing rate is 10 liters per minute. Let me just write the number 10, so we can skip the units for now and leave that for the end. The question is, what's the concentration in? Any ideas of what the concentration in?
0.
It's 0. Why is it 0? It's pure water coming in, right? So there's really no concentration, whether as a percent, molar, your favorite way to express this concentration of salt in chemistry, right? Flow out rate. Well, they're telling us it's coming out at the same rate as it comes in. So it's going to be the same rate, all right? And so that's 10 minus, in this case, the concentration out. But here is the thing. This is actually what changes because, well, the more water that comes in, even though it's at the same rate, the mixture comes out of the tank. So this is what happens because pure water is coming into the tank. This is making the concentration of salt to become smaller every time because what are we getting out of the tank? We're getting a mixture of water and salt. All right, so eventually that salt is going to run out after a while. We don't know when, but eventually it's going to run out. But how are we going to find this concentration? So this concentration, to make it simple, we're going to call it A, which is the mass of the solute over the total volume of the tank. Of course, there's many ways to express concentration, like molarity, normality, depending on the system that you're working. You convert this kilograms of salt into moles and then divide by the total volume to get the molarity. However, well, to make this simple, not to get into too many complicated details from chemistry, we just use the percent concentration, which is usually the most common way to represent this, all right? So again, this is variable. This amount that comes out varies depending on how much salt remains inside due to the fact that pure water is pushing it out, all right? Of course, this term is going to get zeroed out, and we're going to remain with 10 over 1,000, which will be dA dt. Let me continue here. dA dt equals to negative A over 100. And it makes sense to have a negative sign on the right hand side. It makes sense to have a negative rate of change because, again, that amount of salt inside of the tank is getting smaller every time due to water coming in and obtaining a mixture water and salt. All right. Okay, so I think we have all the information to separate variables and solve a differential equation. So I'm going to have the dt on the right hand side and the a on the left hand side. I'm going to keep the negative and the 1 over 100 on the right hand side. I'd rather express it this way. I think it's going to be easier. So dA over a equals negative 1 over 100 dt. All right, so let's see. So let's solve the differential equation. Integrate both sides. So that's ln of absolute value of a equals negative 1 over 100 t, okay, plus c. All right, so this is the general solution for now. This is let's label it as a general solution. All right. So, of course, we cannot work with a general solution containing a C because of course, I mean, if we want to know the amount of salt that remains after, for example, 5 hours, 75 minutes, I don't know, whatever time you want to know, we have this plus C in the middle of nowhere, you know, so we need to find the actual value of C. Well, number one, let's solve the equation. Actually, well, yeah, that's fine. We can get the particular solution from here. So, in order to get a particular solution, we need an initial condition. Remember how we solve a differential equation with some y of 0 equals a number equals 5, whatever number? Well, so it turns out that we have an initial condition somewhat cryptic here, you know? So, and well, so they're telling us that initially, before water comes into the tank, we have 15 kilograms of salt, and that's all the situation about the amount of salt. So after a while, that amount of salt is going to get out of the tank with water until we run out of salt. All right. So that means that in this case, with A of 0 equals to 15, and this is because the initial amount of salt is 15 kilograms. All right, so that's why. So this is what we're going to do. We're going to plug in ln of 15 equals -1/100 t plus c, where in this case this will be 0, this will be 15, and well, so this is going to get zeroed out, and c will be ln of 15. All right, we may go back to the general solution and plug back in ln of 15, or ln of 15 for the constant of integration. That is ln of A equals -1/100 t plus c, which is ln of 15. So we may go about solving the differential, or this equation. This is not anymore a differential equation. This is already the solution. So we can exponentiate both sides. So let's go ahead and do that. Exponentiate, but recall that this affects both terms in this case. All right, and so cancel. And in this case, well, if you think about the context of the situation, I think in this case we can skip the absolute values of A, because A in this case represents amount of salt. So would it make sense to have negative amounts of salt? So in this case, for this reason, we can just cancel A. I mean the absolute value bar. So A equals to e to the -t/100, and by properties of exponentials, e to the ln of 15. And in this case, we can cancel the e with ln, and that's going to give us the expression that we want. A of t equals 15e to the -t/100. So this mathematical model will help us determine how much salt remains after your favorite time. In this case, it's minutes. After 5 minutes, after 15 minutes, after 60 minutes, you know. Let's look at another example. So for the next example, yes. This one, this part? Well, by properties of exponentials, laws of exponents, whenever you have e to the a plus b, this is e to the a times e to the b. Alright, and in this case we have two terms. This is you can think of this as the A and think of this as the B. Alright? Okay, so let's move on to the next example. So what do we have? We have a vat with 500 gallons of beer containing 4% alcohol by volume, and beer with 7% alcohol is pumped into the vat at a rate of 5 gallons per minute, and the mixture is pumped out, of course, at the same rate. So the question is, well, there's a couple of questions. What is the amount of alcohol after an hour, and what is the percentage of alcohol after that same time? So again, let's draw a picture. Let's draw a picture here and write down whatever comes in, whatever comes out. So what do we have? We have 7% alcohol, which in decimal is the same as saying 0.07. And recall that whenever you have information in terms of percentages, we don't use percentages in formulas or equations. We need to convert those to their corresponding versions in decimal. And it's coming in at a rate of 5 gallons per minute. All right, so in this case, what's coming out? So it comes out something at 5 gallons per minute, which is the same rate. All right. But what comes out? Well, it depends on the time, because in this case we're mixing two different beers. One that is 4% alcohol and another one that is 7% alcohol. So at different times we're going to get something that has a certain concentration in this case. So that's actually what varies in this case. Alright, so let's set up the equation again. dA dt, which is flow in rate times the concentration in plus flow out rate times the concentration out. All right, well, so what's the rate in? Number one, for the flow in, yes. Oh yes, I think I said minus, but I wrote a plus, right? Yes, thank you. So flow in rate and flow in rate. Well, they're telling us this mixture is coming in at a rate of 5 gallons per liter. And again, I'm gonna skip the units just so we don't have a lot of symbols and numbers in our equation. And well, this time what the concentration in is, it's going to be different than the previous problem, because in the previous problem we just had water coming into the tank, water with no solute at all. In this case, no salt, nothing actually. But this time something is coming in. Well, water, which is the water from the beer, plus the 7% alcohol, which is times 0.07. Minus flow out rate, which is also 5, times the concentration in which it comes out. Well, again, that's what varies, just the same way as in the amount of salt in the tank from the previous problem. The amount changes, the amount that comes out of the tank is different at every single time. Well, let's call that A, over the total volume in this case. Well, so that's going to be 500 gallons. Simplifying this equation, we get 0.07 times 5, that's 0.35, and 5 over 500, let me call this, okay, 1 over 100, or 0.01 A. So that's the equation that we need to solve in this case. Alright, so let's separate the variables. So multiply both sides by dt. So dA equals 0.35 minus 0.01 A. Oh, oops, that the A goes here. dt, and that factor that contains the a, I'm going to move it to the left hand side by dividing both sides by that. That's the a over 0.35 minus 0.01a. That equals dt. And in this case, we're ready to go and integrate this equation. Integrate both sides of the equation. That's the integral of dA over 0.35 minus 0.01a and the integral of dt. All right, so the right hand side of the equation, that should be a really easy one to do. And however, the left hand side will require a mini u substitution. So let me show you that u substitution. So that u equals to 0.35 minus 0.01a. du equals negative 0.01 dA, which means dA, it's negative 1 over 0.01 a. So that's going to be the correction factor for the left hand side, and well, so that's going to give us the integral of negative 1 over 0.01 du over u, and well, we can integrate the right hand side. That's t plus c. All right, let's take a couple steps to simplify the integral on the left hand side. Let me take out the constant factor out of the integral so we can easily see the rule that we're going to use to integrate du over u, which again is going to be a natural log. So negative 1 over 0.01 ln of u equals t minus c, or t plus c. So now we need to back substitute for u in this case. And u, recall that we set it up as 0.35 minus 0.01a. So negative 1 over 0.01 ln of, well, in this case we don't need absolute values because again we are dealing with positive quantities, so that's fine because it's a physical, these are physical amounts, it's amount of alcohol, so there's no such thing as negative quantities, you know. So 0.35 minus 0.01a, and that equals to t plus c. So we're essentially, or we're almost done getting the equation, or rather the function. So let's keep solving for a in this case. So let's multiply both sides by negative 0.01 that's going to give us the following. That's ln 0.35 minus 0.01a, and that's well, on the one hand, check this out, number one, it's going to be negative 0.01 t, but recall that by absorption, when we distribute these multiples over an arbitrary constant that is yet to be determined, that just remains a c again, all right? It remains a c. And then from here, well, let's try and get the a by itself. In this case, well, we need to get rid of the exponential, then we need to get rid of, the natural log, then we need to get rid of the 0.35, and then the negative 0.001. And we get this done by exponentiating both sides. And again, recall that this affects both terms on the right hand side. Now, just to cancel, 0.35 minus 0.01a equals e to the negative 0.01t, and by the same law of exponents that we used last time in the previous example, rather, that's just e to the c. And well, again, e to the c, e to the number that we don't know what it is, it's just an arbitrary constant, that's just c. E to the negative 0.01 t. So that's a 0.35 minus 0.01a. And well, we can go about solving for A, subtract 0.35 on both sides. That's going to give us, leave us with negative 0.01A equals C e to the negative 0.01T minus 0.35, and dividing both sides by 0. Let me go up here. Okay, let me go. Okay, let me stop here. So A equals to number 1. Okay, so when we divide both sides, or all terms on both sides, by negative 0.01, in this case, so cancel here, cancel the negative 0.01s, and again, a constant divided by any number, it's still a constant. So e to the negative 0.01 t. And negative 0.35 divided by negative 0.01, that should be a positive 35. So that's our general solution to the differential equation. Of course, we need a particular solution based on an initial condition in this case. All right, but the trick here is, how are we going to get the initial condition? In the previous example, we have an initial amount of 15 kilograms of salt in the mixture. What do we have this time? So let's find out. All right, so this one is going to be a little tricky to get, because notice in this case they're not telling us the amount of solute in the solution inside of the tank. They're telling us the concentration per volume, by volume of alcohol in this case. So number 1, so to get the initial condition, so something to keep in mind is, number 1, let's recall the formula to find the concentration by volume. So in this case, percent by volume is the volume of the solute over the total volume times 100%. And let me label this. This is something you have done in your chemistry or basic science course. As you know, percent is the amount of solute divided by the total. So that represents the solute, and that represents the volume of the mixture, the total volume. All right. So what do we know in this case? So they're telling us in this case we have a 4%. So that's what we have initially, right? Initially we have inside the vat with 500 gallons, we have alcohol, we have beer that is 4% alcohol. So let's use that as our piece of information. Well, the volume of the solid, we don't know what it is. That's where we're going to find out. Over the total volume, which is 500 gallons, that times 100%. So number 1, if we divide both sides by 100 and solve for Vs in this case, well, that's going to give us, okay, let's multiply both sides by 500. That's going to give us volume of the solute times 100% equals, well, let me skip the symbols. It's going to be 2000, and the volume of the solute is in this case it's going to be 20. All right. And what does that represent again? Represents the initial amount of alcohol. All right. And well, this could be, it's actually gallons. So that's what we have inside of the tank at the beginning, before the other beer comes into the tank. It's 20 gallons of alcohol contained inside of 500 gallons of beer, right? That is before the mixture. All right, so now that we have that initial amount of alcohol, we can obtain, or we can call this an initial condition. From here, the initial condition with A of 0 equals to 20, that is the initial condition. We can go about and find that concentration of, or that, I mean, not the concentration yet, but actually the constant of integration. So that's going to be 20 equals C e to the negative 0.01 times 0 plus 35. So, number one, negative 0.01 times 0 is just going to be 0. And e to the 0, that's just going to be a 1. And well, so what do we have? 20 equals to C plus 35. And in this case, C will be equals to negative 15. So we may go about the equation that we wrote in general form to its particular form. A of t equals 35 minus 15 e to the negative 0.01 t. So that's the mathematical model that we will be using to find the amount of alcohol at any particular time after it's okay, this is set in minutes, after 25 minutes, after 35 minutes, you name it. So that's only the first part of the question here. Now they're asking for part B. What is the percentage of alcohol after 1 hour? So be careful, because, well, what are we going to plug in to know the amount after 1 hour? What are we going to plug in for T? Yes, but since in this case it's an hour, what's the value of T that we should plug in this case? 60, right? Be careful with the units, because this equation was solved taking into consideration a rate of change in terms of minutes. So if they're telling us 1 hour, then we have to do A of 60. That is 35 minus 15 e to the negative 0.01 times 60. And after simplifying this madness right here, this should be A of 60 equals to 26.77, and in this case we can put the units gallons, right? And well, so they're not asking us for the amount, they're asking us for the concentration. All right, they're asking the percentage of alcohol after 1 hour. So what do we have to do? In this case, divide, use the percent volume. Let me add one more page. So, so the percent by volume will be the volume of the solute over the total volume times 100%. And in this case, all we have to do is divide this number right here over by the total volume, which in this case is 500 gallons. 26.77 over 500 times 100%. And when we simplify this, this should be 5.35 alcohol. All right. So here's the picture. So suppose you guys are going to go into the beer business. You know, now that it's a very common business to come up with craft beer, and you want to make a mixture of beer. So here is a way to determine how much of one beer and the other beer do you need to mix together, and at what time do you need to to stop the mixture so that you get a new beer, a blend of beer that is 5.35%. So if you wanted to find, for example, well, I want to make these two beers and come up with something that is, I don't know, 6.93% because of regulations or whatever it is. So you need to solve this equation for T to find out when do you have to stop the mixture inside of the vat so that you get that desired percentage, all right? And this is the end of this section. Let's touch base on real quick on models of population growth. And one of the simplest population models right here is the one that you have seen in pre-calculus, in where else, intermediate algebra, you name it. And I think I mentioned this not too long ago when we started this chapter. And well, the most simplistic population model is that want to tell us that the rate of change of the population with respect to time is proportional to its size, right? So depend how big or how small this population size becomes depends on its size initially. So, and the initial condition is that at the beginning, P of 0, it's just P initial, whatever initial population was in that community. So we're going to solve the differential equation right here by separation of variables. So dP dt equals Kp. So solve dP over P. That is, I'm going to divide both sides by P and multiply both sides by dt. And we're ready to integrate the equation. And once we get the solution to this equation, the model that we're going to obtain is going to be very familiar to you. So the integral of dP over P, that's going to be ln of P. And in this case, I'm not going to use absolute value bars because it's amount of people. So there's no such thing as negative amounts of people. So that's Kt plus Kt plus C. And doing the same as we did before, exponentiate both sides to get P by itself. So that's going to be P equals to e to the Kt times e to the C. And again, e to the C is just a number raised to an arbitrary constant that is just the constant, C e to the Kt equals to P. So this is so far our general solution. All right. Now, we need to use the initial condition here in order to find that particular solution. So using this condition, so that means x equals, or rather, t equals to 0 and p equals to p initial. So P equals P initial equals C e to the K times 0. But again, K times 0 is just 0, and then e to the 0 is just 1, and 1 times C, that's C equals to P initial. Coming back to the general solution, plug back in what we had for C, and that's going to give us our particular solution, P of T equals P initial e to the Kt. And of course, you've seen this model before. It's the exponential model. Well, in this case, K, depending on the value of K, or rather the sign of K, is if K is positive, well, that's going to model growth. But otherwise, if K is negative, that's going to model decay, you know, like radioactive decay, or like in Newton's law of cooling, so decay in the temperature. Well, we're going to do one example next time, and then we're going to look at the